think it must be morning in the US, right? Good morning.
Yes, thank you. Yeah, it's early morning here because
very early morning. Yeah.
Yeah. So it's very nice to meet you finally. Of course, I've known about you ever since that remarkable proof of primality being in P, but never had the pleasure of meeting you.
Yeah, and I know you very well from your books, which I regularly use.
Thank you.
Yeah, really comprehensive content. And especially periodic analysis, I use a lot.
Thank you. Yeah, and I sometimes when I talk to people, especially in developing countries, I mention the remarkable work that you and the students did at IIT because it's encouraging to people to know that you know, it's not only in the wealthy countries that breakthroughs can occur that have very broad impact.
Yeah, sure. In fact, this workshop commemorates already a person who was of that type.
Yes, of course. Yes.
Yeah. 100
yes,
years
but
ago.
I think it's important to illustrate that that's still happening. That, you know,
Yes.
Ramanujan was not the only one who made remarkable advances. You know?
Yeah. No, Ramanujan, of course, worked in far more impoverished conditions than we ever did.
Yeah.
So he's stellar, exceptional, unparalleled.
Yeah, I always talk about him, and I teach a course in the summer on history of mathematics, and I always talk about him along with Sofia Kovalevskaya, whose picture is in back of me.
Right,
now,
I heard, yes.
As examples of people who came from sort of unexpected backgrounds, because at that time in the 19th century, Russia was a relatively poor, backward country, or at least that's what it was viewed as. So people were very surprised when a woman who, and women were very much repressed in those days, when a woman was able to come out of such a country and then accomplish these things. So I talk about Kovalevskaya and Ramanujan in the same way, in a way.
Yeah. So I think we start in 1 minute.
Okay.
Good evening and good morning to the speaker. I invite Professor Nitin Saxena to introduce the speaker. This is the plenary talk number 14 by Neil Koblitz. Nitin.
Yes, thank you. So it is my privilege to introduce Professor Neil Koblitz. He did his PhD from Princeton in 1974. And with a 4-year stint in Harvard, he joined as faculty in Math Department in University of Washington in 79, where currently he's a professor, and he's also an adjunct faculty in University of Waterloo. He created the hyperelliptic curve cryptography, and he also co-created the basic elliptic curve cryptography itself. He has written very well-read, well-known books, especially about p-adic analysis and elliptic curves. And I myself use these all too often. And I especially recommend everyone to read his opinion pieces on the various thorny issues related to society, education, and global politics even. He has some very interesting stands and opinion pieces that you can find even on his homepage. So yeah, I welcome him, and please, it's over to you, Professor Neil.
Thank you very much for the introduction. And I want to start by thanking the organizers for inviting me to speak. It's truly an honor to speak at this commemoration of 100 years since Ramanujan. I have a large personal debt to India. I spent a year in India as a child with my family when I attended the second grade, or second standard as it was called, in Baroda, India, where the mathematical level of teaching was higher, substantially higher than in my school in the United States. And then when I returned to the US in the third grade, my American teachers mistakenly misinterpreted my ability to multiply together two three-digit numbers as an indication of talent in mathematics. And so they encouraged me, and this is beneficial to me and got me started toward a career in mathematics. And then as a teenager, I was inspired by the chapter on Ramanujan in James R. Newman's book, The World of Mathematics. So I have a big personal debt to India. G.H. Hardy famously said that number theory is gentle and clean. And I think one can extend that to all of theoretical mathematics, which studies a world of Platonic ideals and does not make bold claims about applicability to practical human problems. However, in applied areas of mathematics, the situation is sometimes a lot messier, and mathematics is not always gentle or clean. So that's what I'll be talking about today. And let me summarize that while I get to the PowerPoint. So I'll start by discussing two attempted applications of mathematics to the COVID-19 pandemic. And then after that, I'll pass on to spend most of the talk on quantum computing and Peter Shor's algorithm for factoring large integers. Okay, so the first example from the COVID pandemic that I want to discuss is an example of a truly disastrous mathematical model that originated in my own university at the Institute for Health Metrics and Evaluation, the IHME. The modeling was done mainly by applied mathematicians who took a purely mathematical approach, essentially a type of curve fitting, with little use of traditional epidemiological methods that take into account variations in human behavior, such as cultural norms, patterns of travel, patterns of social interaction. In the early days of the pandemic, roughly in March, the model predicted that if the US took standard measures, mask wearing, social distancing, and suspension of certain social and economic activities, then the total number of US deaths in the course of the pandemic would be no worse than in a bad flu season, 60,000. And the pandemic would be totally over in 3 or 4 months by the summer. This forecast of the IHME was seized upon by the Trump administration in order to justify Trump's statements at the time that there was no need to shut down parts of the economy, no one should wear a mask if they didn't feel like it, and COVID would be no worse than a flu. Of course, the model was based on unrealistic assumptions and naivete about American society, mistakes that were not shared by epidemiologists at the time. And if the model had any use at all, it would have been to argue for the importance of doing our best to meet the assumptions of the model. Instead, Trump and his sycophants used the optimistic projections to justify violating all of the assumptions that the model was based upon. The number of American deaths is already about 5 times the IHME projection, and the COVID deaths in the US are very far from over. Most of those deaths can be attributed to the incompetent response to the pandemic by the federal government. So a question here is, did the IHME loudly object to the utterly fallacious use of their model by the White House? No, apparently not. it seems that the temptation to just bask in the glory that comes from one's work being featured in the president's news conferences was irresistible. So I just want to suggest that in mathematics, maybe there should be a type of Hippocratic oath that we all have to take before getting our PhD, something about do no harm. My second example of a somewhat questionable mathematical approach to COVID is the claims made by many researchers that with the help of math-based public key cryptographic protocols, contact tracing can be done by cell phone apps rather than by the usual laborious work of human contact tracers. Almost all of the discussion and debate about the best way to do this, for example, at a panel I saw at the most prestigious annual cryptography conference in Europe this past May, centered around preserving individual privacy and security, that is, protecting the identity of people who test positive for COVID. Little attention was paid to the human dimensions of contact tracing, especially the impact on the people who are notified that they've been in contact with someone who tested positive. And almost no attention has been paid to equity issues. Now, Susan Landau is one of America's top researchers on privacy and cryptography. As an expert in this area, she thought that the emphasis on privacy protection in the middle of a pandemic was misplaced, and the emphasis should really be on the impact of contact tracing apps on the people who are most at risk from COVID and the people most impacted by being notified of being in contact with a positive person. In the US, this means the poor and racial minorities. She and some co-authors wrote an excellent paper about this that I have the link to up there. I'll mention just a few of their observations. A key limitation of app-based contact tracing is that they use Bluetooth signals which can travel through walls and other barriers and floors. In the US, it's mainly low-income people and racial minorities who live in close quarters. And it's also the same, mainly low-income people and racial minorities who work in high-contact industries where they cannot work from home, and where they work in very close proximity to coworkers, often separated by barriers. As a result, contact tracing apps will produce many more false positives for those people than for affluent white people. A false positive, in addition to the huge psychological impact of being told that you've been exposed to a dread disease, may mean that the people contacted are required to stop working for either temporarily, or they could lose their jobs. In the US, there's very little protection that would prevent them from losing their jobs permanently, very little support for them. They're already living close to the margins even when they are working steadily. They could be evicted from their apartment, which is a big problem in the US now, and have huge disruptions in their family life. And in some localities, they might get an official quarantine order as well. And such orders cause more difficulty for poor people than for rich people. So once again, I would think that it might have been helpful if the researchers who were actively promoting this solution to the contact tracing problem, if they thought more about the human impact and had taken a type of Hippocratic oath about doing no harm. Okay, so now let me pass to quantum computing, which was described as a theoretical possibility in the early 1980s by 3 physicists, including the Nobel laureate Richard Feynman, and by 1 mathematician, Yuri Gagarin. Gagarin in the 1960s and 1970s was one of the Soviet Union's most prominent number theorists. But by the early 1980s, he had switched his interest to mathematical physics. This possibility of quantum computing started to attract a lot more interest after 1994, when Peter Shor developed his algorithm, published his algorithm for a quantum computer that would factor large integers rapidly. This would break RSA cryptography. That is, in RSA, you have an integer big N equal to the product of two primes, and big N is very large. Currently, the recommendation is that big N should be about of order 2 to the power 2048. So if somebody wants to break RSA, they don't know the factorization, and if they can factor N somehow, then they can break into the cryptography. There's first, in the algorithm, there's first a non-quantum part. There's nothing to do with quantum computation, which is a simple reduction of factoring to the problem of finding the order of a random element X in the multiplicative group modulo big N. So I'll quickly outline, I'll give that proof of that reduction from factoring to finding the order of X, which is actually very elementary, but it's elegant, so I think it's worth going through. I'll assume that the two primes are both congruent to 3 mod 4, that's not essential, so that the multiplicative order of X modulo each prime is either an odd number or twice an odd number. And that means there are two cases. Either the parity is the same, X has the same, the order of X has the same parity modulo P and modulo Q, or they're different. So the two possibilities, each having 50-50 chance for a random X, is that both of those orders are even or both are odd, or else that one, say the mod P order is even and the mod Q order is odd. And what I'll show is that in case 2, you can immediately factor N. If case 1 occurs, then you have to just choose another X. And so before long, you'll end up in case 2, that the chance that you'll have to choose more than 10 random X's in order to get case 2 is less than 1 out of 1,000. So without loss of generality, let's just assume we're in case 2. Okay, so the mod P order of X is assumed to be 2 alpha, and the mod Q order is assumed to be beta, where the alpha and beta are odd. And so in the reduction, we can suppose that we know the mod N order of X, which would be the least common multiple of 2 alpha and beta. So we write it as 2 gamma, where gamma is an odd number. That's the least common multiple of alpha and beta. And then all we do is raise X to the gamma power mod big N, that is to the power half its order. Because we're in case 2, when we raise B to that power, which is half the order of X modulo N, we find that B is congruent to -1 mod P and +1 mod Q. And after that, we can immediately factor N by using the Euclidean algorithm to find the greatest common divisor of B + 1 with N. And that concludes the factorization of N and shows that to factor N, we simply have to show that we can find the order of a random X modulo N. So now I'm ready for the quantum part and some background on quantum circuits. In a classical circuit, the input is a bit string, say an n tuple, this is small n tuple of bits. In a quantum circuit, it's an element of norm 1 in a Hilbert space of dimension 2 to the small n, with the basis indexed by all n tuples of bits regarded as integers from 0 to 2 to the little n. Such a quantum circuit, we say, has n little n logical qubits. We represent a Hilbert space element in a standard way as a sum with complex coefficients, and the asymmetric bracket notation that's used in quantum mechanics for a basis element, where A is the index of the basis element, or in quantum mechanic terminology, the state of the system. Here, as I said, the norm is 1, and the square of the absolute value of an individual coefficient is the probability of observing the basis element, or the state, indexed by A. Now, at first glance, it seems to defy common sense that n logical gates will carry these 2 to the n pieces of information. There are 2 to the little n coefficients there. And this situation is being carried by n logical gates. But that's what quantum mechanics says is what happens. And I think the best way to think about this is not to think of the coefficients as pieces of information that can somehow be extracted, because they're not that, but rather they are probabilities that predict the likelihood of observing the A state. Now, a classical circuit acts on an n-tuple by a network of logical gates, such as NOT gates, OR gates, AND gates, which are building blocks for more complicated transformations. A quantum circuit acts on a Hilbert space element through unitary transformations. The building blocks for these transformations are certain 2x2 and 4x4 unitary matrices that are then tensored with the identity matrix to get 2 to the n by 2 to the n matrices. So I'll describe what they are, since we'll be using them concretely. There are 2 types. One type of unitary transformation acts just on the jth bit of A, of the index of the state, whereas the other type acts on 2 different bits, the jth and kth. So this is how they are. So R sub j looks at takes a basis element and looks at the jth, the bit corresponding to the j place in the basis element. If it's 0, it averages over both values of that bit. And if it's 1, it averages with a negative sign put in for the 1 bit. And the 1 over root 2 is for normalization, so that the norm is preserved. The other class of building block transformations simply take 2 different bits, the j and k bit, where k is greater than j, and look at the possible, the different basis elements. And for a given basis element, if the bit in the j and k places are both 1, then it multiplies the coefficient by a root of unity, and otherwise it doesn't do anything to the basis element if it does not have 1s in both places. So for example, if k is equal to j plus 1, it multiplies the basis element by I. This notation from the matrix is simplified, since remember that we have to tensor with identity matrices to get the actual matrix. As a sort of exercise, we can take the product of the different R's, applying R0, then R1, and so on. And we'll see that if that's applied to the 0 state with all 0 bits, we'll get the normalized sum of the basis elements. So just as an exercise, I'll show this in the case n equals 2. So here we take the 0 state, the 0 basis element, and apply R0 and then R1 to it. When we apply R0, we look at the rightmost bit that is corresponding to sort of the 1's bit in the binary expansion, the rightmost bit, and we average over the 2 values of that bit, 0 and 1, with the normalizing factor 2 to the negative 1/2. Then we apply R1 to that, which looks in each case for each of those 2 basis elements, it looks at the first bit, which is 0, and so it averages again with respect to that bit. And when you put all this together, you get an average over all 4 possibilities for both bits, normalized by 2 to the negative 1. Now, a more interesting transformation, that was one averaging transformation over the basis elements, but a more interesting one is a discrete Fourier transform, which is defined as follows. It takes the basis element corresponding to the n-tuple of bits A, to the integer A, to a sum over all the basis elements with coefficients being a root of unity that's determined by the product of A with C. Now, this transform plays a crucial role in Shor's algorithm, and it's important to note that it can be also constructed from the building blocks, not quite as quickly as the averaging transformation. But what you do is you take the same product of the R's and insert S's between them, where after applying R sub j, you apply all the S's whose first index is j. The resulting transformation is essentially the above Fourier transform. And note that it only takes n different applications of the R transformations and n times n minus 1 over 2 applications of S transformations to do this. So it's quite feasible. And what you get is essentially the Fourier transform, although there is a minor technical issue that you have to reverse the bits of A for this to work out exactly. So here's an example when n is 2, and I'm taking A to be the bit string 1, 1, the number 3, where of course we don't have to worry about reversing the bits. And so here we first apply R0, then S01, there's only one S in this case, and then R1. So if we apply R0, because the rightmost bit is 1, we get an average, a type of average over the two possibilities for those bits, 1, 0, 1, 1, but with a negative sign inserted. And then we apply S01, which just takes that term with the 1, 1 basis element and multiplies it by I. And finally, we apply another averaging transformation R1, which again this time looks at the leftmost bit, and because it's 1 in both cases, we get some negative signs in. And when you put this all together, you get precisely the Fourier transform of applied to the basis vector 1, 1. Okay, so now to factor big N, we saw that it suffices to find the multiplicative order, which I'll call R, of a random x modulo n. And if it doesn't work, then we choose a different x. We have to choose an x that's in case 2 for it to work. Now, little n will be chosen so that 2 to the little n is of order of magnitude big N squared. So in the case of RSA with 2048-bit moduli big N, we're thinking of little n's being somewhat more than 4,000. For each j less than n, we compute on a classical computer. This is a very easy, very quick computation. We raise x to the 2 to the j power mod big N. We're preparing for doing modular exponentiation by the repeated squaring method. Now, these numbers, big N that we want to factor, are random x, along with all of the 2 to the j powers of x mod n. There are somewhat over 4,000 of them, are fixed for. We're absolutely fixing them, and we're not even storing them in the quantum computer's memory. The reason why is that there's no way known to construct memory for a quantum computer to input large amounts of data. Fortunately, we don't have large amounts of data by standards of computation. We just have a few thousand data points. So what we do, since we don't have a memory, what we do is we construct this circuit array specially tailor-made for those 4,000 or so values. And this would be done in practice by a classical computer, would rearrange the circuit for the particular values that we're interested in of n, x, and the powers of x. Now, using the repeated squaring method for modular exponentiation, the quantum computer can then easily compute any power of x modulo n for any modulo big N for any n-bit integer a, and then place that and then put that value as the index of a state. Look at that state. That is the the least residue of x to the a mod big N to go to that state. And it can do this simultaneously for all a. And that's what takes some time to get one's head around that. So if little n is over 4,000, we're talking about more than 2 to the power 4,000 modular exponentiations. Now, I'm not going to try to explain the experimental justification for thinking that a quantum computer could do this. Quantum mechanics itself has been verified extensively by experiment, but nobody knows whether this type of phenomena can be produced on a large enough scale of space and time and in a controlled way so as to give reliable computational results. I'll get to that later. Okay, so now with this background, we're ready for the key steps in a quantum algorithm to find the order of x mod n, mod big N. The computer has 2 registers that are entangled. Quantum entanglement plays an essential role in the algorithm as it does in quantum mechanics generally, and it's represented mathematically by the tensor product. At first, both registers are in the 0 state. Then register number 1 is changed to the normalized sum of all the states. This sort of averaging transformation is applied to the first register. Then the combined system of registers 1 and 2 is changed from the sum of all the states, each one tensored with the 0 state, to the sum where in each summand we replace the 0 state on the right by the state indexed by the least residue of x to the a modulo big N. So this is where the computer simultaneously replaces the 0 state by these states that correspond to a that are different for different a's. Okay, and finally we apply the Fourier transform to the first register that will produce the system given below here. This is a sum, a double sum, because in the first, when we apply the Fourier transform to the basis element indexed by A, we get a sum over C. Okay, so this is what we're going to look at now. And we're going to ask for a fixed, look at a fixed pair of basis elements on the left and right, the state C on the left and the state B on the right. So we want to fix x to the a mod n. We want to fix the least residue of x to the a mod n. So we're going to look at the subsum of this with C fixed and also with the basis element in the second register fixed as well. That is, A is fixed, is in a fixed congruence class U mod R. So U is fixed, a fixed residue mod R, and we just sum over A in that congruence class. So that means for a fixed B, a fixed value of the second basis vector there, the basis vector in the second register, this is the coefficient we get. So that sum is only a small part of our original double sum, obviously, but it has a huge number of terms nonetheless. Because recall that little n was chosen very large. It was chosen of order big N squared, much larger than just big N. And so the number of terms in the sum is 2 to the little n divided by R, since we're summing over just one congruence class mod R. And since R is less than big N over 2, this means that the sum has at least 2 times big N terms, which is a huge number, like 2 to the 2049 terms. Okay, so here's the coefficient. We want to look at the coefficient in the outer parentheses there, and get an idea of how large it is. There are 2 cases to consider. One case is when R times C. R is the order of x modulo big N. So one case is when C times R times the order of x modulo big N is not close to 0 mod 2 to the n. In that case, if you look at that term, the phase angle inside the exponential, as a varies by multiples of r, so we take a equals u and then keep adding multiples of r to it, what we're adding to the phase angle there is multiples of rc over 2 to the n. And if that is not very close to being an integer, what happens is the phase angle varies around the unit circle. And so we're putting in roots of unity that are all over the unit circle, and we'll have a lot of cancellation, and the coefficient will be relatively small. So that's one case. And that occurs if the amount we're adding to the a's, as we vary the a's, that's r, multiples of r times c divided by 2 to the n is not close to, very close to an integer. On the other hand, if that product is very close to an integer, then the phase angles go up by integer multiples of 2 pi I, close to, not exactly, but close to integer multiples of 2 pi I, and the roots of unity point in roughly the same direction on the unit circle. And so instead of canceling, they accumulate hugely and give us an extremely large coefficient. So, and this is really the last step in the algorithm. It's called quantum phase estimation. And the point is that an observation of the system will have a very high probability of seeing a state, a basis element in the first part of the tensor product, in the first register. In register 1, when we observe the system, we're very likely to see a value c such that c times r is extremely close to 0 modulo 2 to the n. And taking into account the huge magnitude of these numbers, when you see what this tells us, it will allow us to determine r. So because the CR really has to be extremely close to 0 modulo 2 to the n, not just very roughly. So R will actually be determined exactly with high probability. So that concludes the algorithm. And notice that it's not, conceptually, it's not a very complicated algorithm. And yet it does have this, this feature that it's challenging to get one's head around the idea of computing 2 to the 4,000 plus modular exponentiation simultaneously. Let me mention that Shor's algorithm can be modified to solve the elliptic curve discrete log problem upon which all elliptic curve cryptography is based, just as RSA is based on the presumed hardness of the factorization problem. So if a large-scale quantum computer is built, it will make obsolete all currently widely deployed public key cryptography. But that's not a cause for alarm, because there's been a lot of work recently, in recent years, on developing alternative types of public key cryptography that are based on problems that, as far as we know, are not easily attackable by quantum computation. This work still, there's a lot of testing and debates going on over which method of so-called quantum safe cryptography will be the best. And then there has to be a standardization process. So it'll take some years, but it'll certainly be done in time, probably long before there's any quantum computer around to worry about. Now, there are formidable obstacles to construction. Shor's algorithm requires two 4096 qubit registers to factor an RSA modulus of recommended size. Because remember, little n had to be twice the bit length of big N. And this doesn't account for all of the gates that we need to incorporate the values of big N, X, and all of the 2 to the jth powers of X, like over 4,000 powers of X into the circuit. So there'll be many thousands of logical quantum gates that will be needed to attack RSA. It's estimated that each logical gate will require several thousand physical gates, because you need a whole lot of physical gates to achieve a reliable logical gate because of the extreme amount of noise and instability in a quantum system. Each logical gate has to produce a very reliable output using error correction and statistical analysis based on what's happening in thousands of physical gates. So that means that many millions of physical gates would be needed in order to factor big N. And even a small amount of scaling involves obstacles connected with shielding and coherence that have not yet been overcome. It's fair to say the physics and engineering challenges are far greater than the ones that confronted the developers of the first modern electronic computers. They seem to be of a magnitude much greater than those encountered in the Manhattan Project to develop nuclear weapons and the Apollo Project to put humans on the moon. And the time scale in order to accomplish all this is also likely to be much longer than in those cases. And the eventual outcome is far from certain. And it's very controversial, what the chances are this will all work. We also have to ask how important would quantum computing be if it is achieved? And there, the key question is there a killer app? By a killer app, we mean an application that's of sufficient practical value to justify the investment of large amounts of money in developing this. And then the companion question is, well, how soon and how much of an investment of resources will it take to develop a large-scale quantum computer, say, capable of breaking RSA? Well, in fact, there's no clear-cut killer app known. Cryptography is not a killer app because if quantum computers are ever close to becoming a practical reality, everyone will switch to these new forms that I mentioned of so-called quantum safe mathematical cryptography. And at that point, quantum computers will be of no use to hackers trying to steal your credit card numbers or to national intelligence agencies wanting to steal your secrets. The most authoritative report that I've seen on this whole issue was released a little less than 2 years ago by the US National Academies, called Quantum Computing Progress and Prospects, that expressed a lot of doubt that private funding of quantum computing would continue for long unless convincing applications were found. Despite the lack of killer apps, known killer apps, the promoters of quantum computation continually make very exaggerated claims about its future use. It's not surprising that scientists who need to have generous corporate funding of their work would exaggerate its usefulness. In addition, the companies themselves, since we live in a capitalist consumer economy, they communicate with journalists and with the public using a tremendous amount of hype, of exaggeration. But even taking into account this tendency toward hype, the claims made for quantum computing are extreme. They say quantum computers could one day provide, this is IBM, could provide breakthroughs in many disciplines, materials and drug discovery, the optimization of complex systems and artificial intelligence. And then from Microsoft, quantum computing takes a giant leap forward that will forever alter our economic, industrial, academic, and societal landscape. This has massive implications for research in healthcare, energy, environmental systems, smart materials, and more. Well, and this all where they don't even know how to input large amounts of data into a quantum computer. It's not even known theoretically how you could do that. Well, in the US, after 4 years of the Trump administration, we tend to have a sort of internal meter that alerts us to false statements. And so this is what my internal meter says about these statements from Microsoft and IBM. So the answer to the question of when, how long, how difficult will it be to construct this thing is also unclear. A common prediction 5 years ago was that in 15 years, by 2030, there was an even chance that it would be built. It would cost over $1 billion US and would require the energy of a dedicated nuclear power plant. And many think that this is far too optimistic and it would be many decades or centuries before this would be done. But to give them credit, the optimists are at least consistent. Just this past October, I heard from some of the same sources that the current prediction by promoters is that there's an even chance of a large-scale quantum computer being constructed in 2035, 15 years from now. So they consistently seem to be predicting 15 years into the future. Well, over-optimism is natural for people who work in a given area, but this hype can have negative effects. It can divert attention and resources from more pressing needs, and it can give an excuse to people who are using antiquated cybersecurity, for example, RSA with values of big N that are far too small key sizes. And they can use the excuse that they're waiting for quantum safe systems, which are just around the corner, to be tested and standardized. And so it can cause great security problems in the short run while they're sticking with these antiquated systems. Finally, I want to conclude with a discussion of how good we are at predicting the future. A group of people who spend their lives trying to imagine a future world are science fiction writers. So if we go back to the golden age of science fiction in the 1950s and 60s, what were they predicting? Let's compare what they were predicting to what's actually happened. In the area of interplanetary exploration, the prediction was by the year 2000, we would have colonies on the moon and Mars and maybe some moons of Jupiter and Saturn and maybe mining operations on the asteroids. These are very typical predictions from the golden age. The reality is that a half century ago, there was a 4-year period during which 24 humans ventured beyond Earth orbit through the Apollo project. 12 walked on the moon and 12 flew near the moon. In the subsequent half century, no human has gone beyond Earth orbit. The historic orbit of Yuri Gagarin 59 years ago was followed as the second most exciting moment in human space exploration. After that occurred in 1969 when the first human set foot on the moon. Since then, it's been more or less an anticlimax. Similarly, supersonic passenger travel. The prediction was that by 2000, everyone would travel between North America and Europe in a couple hours, a few hours by supersonic aircraft. The reality is that there was supersonic passenger travel on a very small scale for very rich people for about a quarter century, and then it ended because it turned out to be neither safe nor profitable. And we all remember the tragic crash outside Paris in the year 2000. I think it's fair to say that passenger transportation by air, sea, or car has not changed in any fundamental way in over a half century. And finally, nuclear power, also similar predictions. By the year 2000, nuclear power will have been scaled down to be so inexpensive that we'd have nuclear power cars, nuclear power ovens, and even nuclear powered wristwatches. The reality is that as far as practical everyday life is concerned, there have been no fundamental advances in nuclear power in a half century. On the other hand, some fundamental changes in daily life and technology were not predicted by anyone 50 years ago. Extreme miniaturization of computers, making them available to everybody. Email, the internet, social media. So there were also examples on the other side where technology that we do have was not predicted. So I guess one can conclude that we're not all that good at predicting future technology. So let's just try to speculate. Will quantum computing see fast progress the way classical computing did? Or will it be more like interplanetary space travel and nuclear-powered cars, a nice subject for science fiction, but not a reality anytime soon? Well, as far as cryptography goes, even if there's just an epsilon chance that a large-scale computer will be built within a few decades, we have to worry about any long-term secret whose security depends on public key cryptography. There aren't that many such secrets. Most secrets don't have to remain secret for very long. Your credit card number, it was used 30 years earlier, no longer needs to be secret. Public key signatures need to be unforgeable only for a relatively short time. And most national security secrets are not even protected by public key cryptography, but rather by symmetric key cryptography, which is not vulnerable to quantum attacks. So the conclusion is that while it's prudent to develop and standardize quantum safe systems, we aren't likely to need them anytime soon. Just like in the case of the COVID examples I started with, the mathematical models and contact tracing apps for COVID, the reality has lagged behind the hype. Thank you for your attention.
Yeah, thank you for the very entertaining talk. So the audience can ask questions directly. You can unmute and ask. You can ask a question or make a comment. Okay, so I wanted to remark that this same method can also be used to compute discrete log, to solve discrete log, right?
Yes, basically the reduction of factorization is reduction to a discrete log problem, discrete log type problem. Finding
very specific, yeah, very specific. So that was a to the x equal to 1.
Yeah, right, right.
And
exactly.
a to the x equal to b also can be solved, I guess,
yes,
the same
exactly.
way.
Yes, yes, thanks for pointing that out. Yeah, and that's why it's no surprise that the elliptic curve discrete logarithm problem can be attacked as well.
Yes, right, yeah. So for the elliptic curve, the proof will be exactly the same. It's syntactically the same proof.
Essentially, yes.
Okay.
Yes.
I see. So it probably works for any group, any explicit group that.
Yes, it would also be the Diffie-Hellman problem,
Right.
the Diffie-Hellman key exchange, which is another type of public key cryptography, would also fall to this.
Okay.
Because as it turns out, because of the reduction of factorization to a type of discrete log problem, it turns out that all public key cryptography is based one way or another, or I should say all commonly deployed public key cryptography is based in one way or another on a discrete log problem. It requires some sort of discrete log problem to be difficult. Right. And so there's a strong case for developing and standardizing and deploying types of public key cryptography that are based on completely different types of problems that are totally unrelated. So even if quantum computing doesn't, never becomes an issue, still one can argue that it's good not to have all your forms of cryptography based on essentially the same type of mathematics. And this is it's a bit of a surprise because at first glance it seems like the elliptic curve discrete log problem shouldn't have anything to do with factorization. Mm-hmm. But because of this reduction of factorization to a discrete log problem, actually there is a lot of conceptual similarity, and so that's really the problem.
Yeah, true. So in the chat box, Deeptojit is asking, can this order finding be made classical instead of quantum? Which I guess answer is no.
Well, not that I know of.
Yeah.
This business of computing, or in some sense computing, I don't know whether you want to think of it as really computing, but using, in some sense, making use of every single power of x modulo n. If you've got that, you can just find your answer by inspection. So I don't see how Shor's algorithm, at least as far as I know, there's no way that Shor's algorithm would benefit us with classical algorithms.
Correct. Yeah, and of course there are no general dequantization results known. So you cannot really remove the quantum part from a quantum algorithm. There's no general such result. Yeah.
No, it's really something fundamentally different.
Yes. Any other questions from the audience? So you mentioned one bad COVID model in the US. Now, is there a good COVID model after so many months?
Well, to be fair to the IHME, after their model turned out to be so, actually within about a few weeks of their model, it was clear that it was completely wrong. They modified it. They're still using, as far as I know, almost exclusively mathematical techniques without epidemiology, but using much better data and much better curve fitting. So they've gotten better results recently, and the recent predictions are probably reasonable. But at the very beginning, there were other people. There was a group at Imperial College London, that predicted 480,000 US deaths, which is now looking like that's not far off. It'll probably be more than that, actually, from what I've heard.
Yeah. By March or by February.
But that's the right order of magnitude. In the US, in the Spanish flu pandemic, there are an estimated 700,000 or 800,000 deaths in the US. And I think right now it's looking like we're going to approach the same value. And the Imperial College epidemiologists warned about this. So there were many different groups of people, mainly epidemiologists with assistance from mathematicians, but not exclusively mathematicians who formed interdisciplinary groups and investigated this. And some of them came up with much better models. But of course, those models were not used by the Trump administration because they predicted much worse outcomes.
Yes. There are few more questions in the chat. So is it possible to use isogeny-based post-quantum algorithms for encryption?
Yes, that's one of the main areas that's been developed. Now isogeny-based encryption also uses elliptic curves, but in a very, very different way. It uses and walks through the isogeny graph of a supersingular elliptic curve. There's no known way to attack that using quantum computers, at least no way that would have a huge effect. A lot of times you can use quantum computation to somewhat speed things up, but maybe only by a constant or a very small factor. So that's certainly a contender. Isogeny-based systems and lattice-based systems are among the leading contenders for quantum-safe public key cryptography.
Yeah, Deeptojit is asking a related question. Can you shed light on why lattice-based cryptography beats quantum computation?
Well, the problem is based on the type of problems finding a short vector in a lattice, or variants on that. It's simply that no one has an algorithm similar to Shor's algorithm for that. It turns out that it's very difficult to construct a polynomial time quantum algorithm for a natural problem of that sort, like the short vector problem. And in most cases, nobody has an algorithm. The only major example, as far as I know, of a fundamental type of mathematical problem where you get this absolutely huge speed up from exponential time to polynomial time, as in the case of the elliptic curve discrete log problem. The only case that I know of anyway is the discrete log problem. So it's not that there's anything special about the problems that arise in lattice-based cryptography. It's just that they're not discrete log problems. And so people don't know how to attack it in any way that will have a huge impact by quantum computers.
Right. So I guess what I've heard is that if quantum computers can do discrete Fourier transform for non-abelian groups, then you can solve more. So currently you can do it only for abelian groups. This Fourier transform is really for abelian groups, and non-abelian, you cannot get any advantage by quantum.
Yeah, I'm not familiar with that work.
So for example, the graph isomorphism problem also you cannot solve on quantum.
That's right, as far as we know.
Yeah, right. So maybe the isogeny has the same advantage.
Yeah. Again, as in all these problems, you know, this is all conjectural. I mean, you can't prove that no algorithm will ever be found, really.
Right. Yeah. Right. So it's a big open question whether NP hard problems there is any advantage in quantum computation.
That's right. That's right. There's no major advantage known. So for example, whether there's a polynomial time quantum algorithm for an NP hard problem.
Yeah, sure.
That would be very interesting if that were found.
Yeah.
But of course, a discrete log problem is not NP hard, so
yes.
So we don't know.
Okay. Any last question? Okay, thank you, Professor Koblitz. It was very interesting, very entertaining. Thanks. Have a good day.
Thank you. Same to you.
Yeah.
So thank you, Nitin and Neil Koblitz. It was a very, very exciting talk. But the science fiction predictions like that of Arthur Clarke on WWW came true. So we're very optimistic about the science fiction predictions. Okay, thank you very much.
Okay, thank you. Bye.
Thank you. Bye.